Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody watching us from the future. On Tuesday morning, I arrived to my other lecture, Big Data for Engineers, and switch on Zoom, then update. And then I start the lecture as usual. And then what happens is that it tells me, oh no, we've evolved our product and removed the feature to project the slides. And so we had to find another setup. So now this is the other setup, and it might not be perfect, but we'll try to improve again over time. So today I'm going to take it from where we were last time, which is that we had this special case with a very long list of postings that corresponds to a term that happens a lot. And another postings list that corresponds to a term that is a bit more rare. And that actually happens a lot in reality, because there are words that are very frequent and there are words that are very rare. So this is quite common. And if you consider even a stop word that have a huge list, even more so. And so some people had the idea of a trick to add pointers that we call skip pointers that are like magical highways that directly take you to some of the postings a little bit in the future. And that is an example here where if you are right here at pointer number, I have to get used to that again, pointer number 4, and then you can cross the pointer all the way to pointer number 10, right, to document number 10. And so this is what is called a magical pointer, a skip pointer, right? And so the idea is that we can add plenty of these pointers over the posting list, right? We can have plenty of them. And my question to you was, how long do you think these pointers should be as a good overall rule of thumb? So do you think it should be 42 as always, or the square root of the number of documents, the logarithm of the number of terms, or the square root of the length of the current posting list? Let me look at your answers. It seems that we have a majority. And the majority is indeed the square root of the length of the current posting list. So that is indeed correct. And it means that it's a compromise that we make between two extremes. If we have two short skip pointers, then you are wasting space because the pointers take space and you're not going to gain a lot because since they are short, you're only skipping a few document IDs, right? A few postings. So that's not very helpful. If it's too long, then yes, that's a big gain that because you directly jump far ahead. But the problem is that you can use that less often because you could really only use that if really you can skip so many postings. So a compromise that was made is to take the square root. So if you have 16 postings, for example, in a list, and you put a skip pointers every 4 postings, 25 every 5 postings, 100 every 10 postings. So that's a rule of thumb, right? And since it's only a rule of thumb, if you build the system, of course, you can tweak that and change that. But this is something that worked quite well in practice. In fact, there are even data structures that can have multiple levels of pointers. Like the higher you go, the longer the pointer. And that's especially used in fact, in vector databases. But I'll tell that to you a bit later in the course, right? OK, so this is called a skip pointer. Any questions on that? Skip pointers? All good? OK. So do you remember that I told you the index is called the standard inverted index and that we would modify it? Well, that was it. That was one possible modification of the standard inverted index, adding skip pointers. And now we are going to look at two other possible modifications of the standard inverted index for more use cases. And the first use case that we have is called phrase search. You remember that in the Boolean querying, which is what we studied in the first week, you can enter your queries in the form of terms or words together with and or and not, right? So the Boolean operators. So that allows you to ask for terms to be or not to be in some documents and then to have a complex Boolean query. This kind of system appeared in the 60s, 70s, was commercialized, was used by companies like legal companies and so on. But it has a few shortcomings. It works very well, it's precise and so on. The problem is that when you actually try to use a system like that, what's going to happen is that you will enter a query and then that query might have too few results, right? There's almost no results. So you change the query to make it a bit less filtering and add a bit more, but then you will have you have too many results. And it's very, very difficult with a system like that, Boolean querying, to have a number of results that is al dente, right? That exactly gives you a few results, a few relevant results. So that wasn't it, right? And there was a bit of research to try to improve these systems. And of course, it has improved because in Google, you don't have to enter a Boolean query. You can enter natural words. And so one of the examples of alternate ways to provide a query language for searching is in the form of phrase queries. A phrase query is when you have several words, like a sentence, and you try to find matches of that sentence. So not just a single term, but a whole sentence. And so the way you do it today with the search engine is typically that you add quotes like this, and the quotes are going to trigger a phrase search. The search engines today, they are kind of a cooking recipe, right? So there's not a single language. They just accept a lot of different entries and they switch between them intelligently, right? So, but you can trigger phrase search with these double quotes like here. And so this is what we call a phrase search. Now, does anybody have any idea? First, you could tell me, can we execute a phrase search like this with our standard inverted index? So we change the query language. We don't have Booleans anymore. We have now phrases as queries. Can I use the standard inverted index to do that and give you the results? See a few heads like this. Who thinks we can? Who thinks we cannot? We have a majority that we cannot. And indeed, you are correct. Because in our standard inverted index, we have information on the fact that ETH may or may not appear in some documents, Zurich may or may not appear in some documents, but we don't have any information on how close they are. And that is because we modeled our documents are sets of terms. And in sets, we don't have any order, we don't have any number of occurrences or anything. So this is not enough. I could give you documents that contain ETH and Zurich, but I cannot filter them more precisely to find those that have them next to each other. So there are two solutions. I'm going to go in turn to these two solutions. The first solution is to modify the standard inverted index into a by-word index. And so the idea is that when I build my vocabulary, so you remember that vocabulary, that's the name that we give to the set of all terms. So that would be basically what we have here. That would be my vocabulary, everything we have here. And now, to build our vocabulary, we are not going to take single terms as we did before. We are going to take pairs of terms. So what's going to happen when I index my documents is that I have here the sliding window of two terms, and I slide over. So help ETH, ETH Zurich, Zurich 2, flexibly, flexibly React, React 2, and so on. And so I build exactly the same structure, the same inverted index, but it's no longer standard. Now, here, I have pairs. And these are all the documents here that contain help ETH, exactly in this order. So it's no longer a set of words now, right? It's list of words because we do have information about some order. And so this is the new index we have. Do you agree the index is going to be larger now? Right? Because we have pairs of terms. So that can be quadratic, right? So maybe we don't have all pairs, but in the worst case, it can be quadratic. So the index is much bigger, but now it has information. And do you see now that I can use this index for my query? If I type ETH Zurich, then I can look that up, this pair of terms that follow each other. And now I have an exact set of matches. Who agrees? Very good. Now, how do I handle longer phrases? Right? If I have like now I'm looking for help ETH Zurich to flexibly react. So I could turn that in some sort of Boolean query based on pairs, right? So now I also have my sliding window over my query. I have help ETH, ETH Zurich, ETH2 to flexibly react. And now I'm looking for the documents that contain all of these pairs, right? Who agrees that I will return at least all of the documents that have this sentence in this way? Okay. Who thinks I will return only these documents? Who thinks I might return more? And you are correct indeed. Because we can have false positives. We might have here a sliding window, help ETH, ETH Zurich flexibly react. But the problem is that I might return this document that you see here, help ETH Zurich to introduce techniques to flexibly react. That document obviously doesn't contain the sentence I was looking for. However, it does contain all of the pairs, just because of the way they appear in the sentence. So that is what we call a false positive. Right? So it means that I have to fix that. And so I'm going to ask you, how do you think we can fix these small positives? How do we decrease the number of false positives with phrase queries? Do we just use by-word indices? Do you use phrase indices with bigger tuples of words? By post-filtering the results, there may be still some false negatives, or by using phrase indices with smaller tuples of words? We have. This is the majority answer. Okay. And you are correct, indeed. We can just increase the window of the pair of tuples. We can make it 3 or 4 or more. You could also use post-filterings, but then you could completely get rid of the false positives. You would not just reduce. So this was the answer. The other answer was not completely correct, because you could, by filtering, you would eliminate all of them, all the false positives. Okay. So if I go back to our example here, now let me stretch the window, not 2, but 3. Now I have help ETH Zurich, help ETH Zurich 2, and so on. So this is going to be tighter, because we are going to be more precise here. And we just need to intersect exactly in the same way, but now we have triplets of words. And now we got rid of this false positive. Now it's a true negative, because you see that document now is going to be rejected. And it's going to be rejected because we don't have Zurich to flexibly. Right? Now we have Zurich to introduce, but not Zurich to flexibly. So this document is no longer returned. Did we get rid of all of them? No, we are just having less of them. But you get bigger and bigger and bigger, and you diminish the number of false of false positives. Okay, so that sounds like a solution. We could do that, but there is a problem, is that if it were so simple, so we would increase the size of the window and have, that's called the K-word index, right? We could increase that size. The problem is that now the size of the vocabulary is going to explode. It went from quadratic to qubits, cubic, and so on and so on. So that just is not viable in the number of terms, right? So that's not really a solution, right? So basically, what people do is they use maybe a byword index, and then they would use some post-filtering after that to completely remove the false positives. So two-step process. Note that in a way, LLMs are a bit this idea of having these huge windows of terms, except that it's a compressed version of that. When you train a model, you have a compressed version of the collection that does return some information on the window of terms that appear, right? So you could see it as a next generation evolution of this, which was a dead end, basically. All right. So we have another solution. Solution number one was the byword index or K-word index. Solution number two is a positional index. So that's something different. Now we still have single terms on the left. Are you okay, George? Is it all okay? We have terms on the left, single ones. And what we modify is the posting itself. We used to have just a document ID here. But now we are going to add more than that. We are also going to add the positions of the terms in the documents. So you see here, I have document C. I gave it a letter as an ID just to not confuse with the positions, right? It could also be an integer, of course. So we have document C. That would be, in the former version, that would be just that, just the document ID, and that's it. Now we add here the number of times that the term appears, 1, 2, 3, so the number of occurrences of the term in that document, followed by a list of positions at which it appears, right? So that's what we call the document ID. That's what we call a term frequency, not to be confused with the document frequency that we have here. So a term frequency, and then we have the positions. So this is called a positional posting. That means that we are no longer in the set of words realm, we are in the list of words real, right? So we know the positions. And now we have all the positions of the term in every document. And to give you an example, two, for example, the word here would be in document C 3 times, that's the term frequency, at position 4, 7, and 11. And if I did it correctly, you can see position 1, 2, 3, 4, then 7, and then 11. So we have this information in here. Who thinks that now I have enough information to tell you which documents contain ETH Zurich one after each other, one after the other? Okay, how can I filter them? How do I know? On Zoom, maybe? Nobody? Let me tell you. So we just need to intersect, of course, as we did before the postings ETH and Zurich. So we intersect them. And now what's going to happen is that we look at the positions here. We also kind of intersect them, but with an offset. So we are looking now for the positions that are exactly +1. So we have 2 and 3. Now we know that document C contains ETH and Zurich, right? It's the same algorithm, the intersection algorithm, except that instead of testing for equality, you test for an offset of 1. Who is with me? Who agrees? That tells us the results? Most of you. Okay, awesome. So this is called a positional index, and that is yet another variation of the standard inverted index. So you see, we have the standard inverted index. We can extend it with skip pointers. We can choose to have byword or keyword indices by having tuples of terms in the vocabulary on the left. And we can choose to extend the postings with positions. And this is when we call them positional postings for this reason, right? Instead of non-positional posting. So basically, if you look here, every one of these places is a positional posting. This is a positional posting. This is a positional posting. This is a positional posting, right? It's a triplet with the term, the document, and the position, positional posting. And in fact, that's it. So this is that corresponds to chapter 2 of the book. Who is reading the book? You should, right? It's very important. It's the same material, more or less, that I'm telling you in the lecture, but you should really read it because it gives you another angle explained by other people, and that's a good complement. And by the way, it's exam material also, which is also a good reason to read the book. There's a few copies in the library of the department, and you might also be able to find it online via the ETH library. All right. Yes. We basically will cover term frequencies in maybe 3 or 4 weeks with what we call the vector spaces and the vector space model. So this is actually the reason why we have document frequencies and term frequencies. They will do a big comeback in the vector space model week. We do not have to, right? We could also absolutely build our own version of a positional index without the term frequency and with just the positions. That would absolutely be fine. But we'll see with the vector space model why it actually also is useful to have the term frequency in there, right? So that's a big cliffhanger for the vector space model week that we'll have later. It's all connected. All right, so that is the end of this lecture. No questions? Okay, and then move on to the next part. Let me stop the recording.